Hello, my shimmering stars. Today, I, Shaurya Grover, welcome you all to this amazing platform of PW Gulf. Students, I welcome you all to your Triumph batch, and today we are going to revise your chapter Solution under the Ultimate Recap session. So, ma'am, what is ultimate recap? You very well know we have already discussed our solid state chapter. Now it's turn for solution chapter. What are we going to do? How are we going to proceed? You are very well aware of it, right, students? So what are we going to do in this particular session today? Again, repeating the same thing. First of all, I will be telling you that which topic, of your this particular chapter are really very important. So whensoever you have an examination, you have to revise that topic first. And afterwards, students, one by one, we are going to revise, we are going to do the ultimate recap of the complete chapter, topic by topic. Yes. So before starting, students, there is a beautiful quote for you all. Do listen to it very carefully. Don't be pushed around by your fears. Don't be pushed around by your fears. Be led by the dreams in your heart. Okay, so your dreams only will take you further, not your fears, students. So if you have any fear regarding any of the thing, any of the topic, or any of the syllabus, or any of the backlog, just forget it. Just believe in yourself. Just look up to your dreams. Okay, and think that yes, I have to do something in life, and for that something in your life, you have to come out of your comfort zone. Yes, students. So let us start this session with a very beautiful smile. So as I've already told you, first of all, I'm going to tell you the most important topics, or I would tell you that if you're going to scroll up the previous year question papers, you are going to see the analysis that yes, these topics are the one from which questions are asked again and again. Right? So let me show you that topic again, repeating. This is solution chapter under your Triumph batch, the ultimate recap session. So first of all, here are the topics that we are going to cover today in this particular session. I'm not only going to cover the most important topics, but also the topics which are, provided in your syllabus. So starting with the very first topic, we are going to do the introduction session, right? That means here we are going to understand about what is solute, what is solvent, and then further moving on to the next topic, we are going to see the types of solution. What are the types of solution? Now, solution can be further categorized under two classifications. So we are going to do that as well. Moving on to the third topic, we will be having the concentration terms. Now, this particular topic you shall be observing in your class 11th also, students, and in your class 12th also. So this topic, if you have done in your class 11th, that's really very good. You are going to brush up your concepts again, and if not, then it's again a benefit for you that you have done in this chapter and it is revised for your class 11th as well. Moving on to the next topic, we will be understanding about solubility and saturated solution. The further next topic will be about solubility of solid in liquid, solubility of gas in liquid. Then is Henry's law. Okay, with regard to pressure and mole fraction, you are going to understand about it. Then moving further, we will be understanding about vapor pressure, Raoult's law, ideal and non-ideal solution. See students, over here the eighth part I would say is really very important with regard to your chapter solution. Very important, students. Moving on to the next one, we'll be having colligative property. Again, the most important segment of your solution chapter, if I shall be talking about. Over here, we'll be understanding about relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, osmotic pressure, all of the four colligative properties we shall be understanding from the very detail, from the very basic. Okay. Now, as I've already told you, these are the colligative properties. Last topic will be about Van 't Hoff factor and abnormal molar mass. So, these are your topics that are provided to you in your syllabus. Moving on to the next part, first of all, let me show you that what are your topic-wise analysis. So, the most questions, if I scroll up the previous year question papers, I observed over there that many of the questions, students, maximum questions are asked from colligative property, determination of mass, and abnormal molar mass. The last segment of yours, okay? So, this basically is a really very important part, really very important. Moving on to the next one, questions are asked from ideal and non-ideal solution. Okay, and then questions are asked from expressing concentration of solution. Now this topic, expressing concentration of solution, is again that topic which I've already told you, you have done in your class 11th also. Okay, and then the next from which questions are asked, that is vapor pressure of liquid solution. So these I have arranged as per your maximum questions from which topic are asked. So the maximum are asked from this, then this, and at last from this topic. Okay, so this is the criteria from where they have asked a lot of questions. And yes, though there are some more topics which are not mentioned over there, but yes, they are so related with all of these that if you don't understand them, if you don't learn them, you won't be able to understand this. So for that, I'm going to complete the whole chapter in this particular session today. Be prepared with your, notes. If you have, then it's well and good. If you don't have your notes, take out your NCERT. If you don't have your NCERT, take out a sheet of paper and a pen and just a bottle. That's it. And just keep on writing. Okay, you can write, you can prepare your notes in a short form over here from this session as well. So let us start with the very first topic of ours for today, that is going to be introduction. What is a solution? Students, what do you feel is a solution? Basically, students, solution is a homogeneous mixture. It is the homogeneous mixture of two or more substances. Now, ma'am, what is two or more substances? What are the two or more substances? See, if I have to define you solution, I would say solute and solvent, when they combine with each other, they form solution. A very simple, a basic definition, which I guess you all also know. Ma'am, you have just spoken two words, solute and solvent. What are these now? See, I told you that when solute students combines with solvent students, it forms a solution. Yes, this is what I told you just right now. So over here, I told you two basic terms. What is solute? What is solvent? And how do they form a solution? For example, students, if I am taking a particular substance and I am mixing it with another substance, so that is what is a mixture of two or more substances. Now I am taking that in a particular amount and a fixed amount, that is a homogeneous mixture. So a homogeneous mixture of two or more substances is referred to as your solution. Solution basically comprises of solute and solvent. Now coming to these two definitions, that what is a solute, what is a solvent. Understand, I can define solute and solvent on the basis of two definitions. The very first definition that I can give to solute and solvent is, solute is the one which is present in less amount. Solvent is the one which is present in more amount. So what I can say is, solute, students, is the one, it is the one which is present in less amount. Okay, and if I'll talk about what? If I'll talk about solvent, students, if I'll talk about solvent, it is the one which is present in more amount. So this is the first definition which I have, written on the basis of quantity. The one which is present in less amount is solute, the one which is present in more amount is solvent. What is the another definition, ma'am? How will you define solute and solvent? Since solute is the one which is being dissolved into the solvent, and solvent is the one in which solute is being dissolved. Are you getting my point? Okay. So let us write these definitions also over here. Solute, it is the one which is being dissolved in the solvent, and solvent is the one in which solute is being dissolved. It is the one in which solute is being dissolved. Clear, students? So this is the very basic with regard to what is solute, what is solvent. Now we very well know what is a solution, right? When we combine both of them, it forms a solution. But now how we are going to classify solute and on the basis of solute and solvent? So let us do first of all the classification based upon the number of solute and solvent particles. So see, students, if I'll talk about types of solution, the very first type we'll be talking about is binary solution. Which type of solution? Binary, in which we have one solute and one solvent. We have two components, one solute and one solvent. That is a binary solution. Okay, now example of binary solution is salt dissolved in water. Salt dissolved in water, right? So salt is here your solute and water is your solvent. Now comes your ternary solution. Ternary solution, name itself says that it has three components. Now what are three components? Always remember, solvent is always one. Solvent is always one, students. Solute can be 2, 3, 4, 5, 6. Solute is the one which you are dissolving, but solvent is the one in which you are dissolving. So solvent will always remain one. Solute will be the one whose number can change. On the basis of the number only we have divided, we have classified solution. See, binary is the one in which one solvent, one solute. Ternary again one solvent, but solute over here will be 2 in order to make the number 3. So 2 solute, 1 solvent. Now what is the example? Example is salt and sugar both dissolved in water. Okay, now next comes quaternary solution. Quaternary solution, the name itself says, ma'am, 4. 1 solvent, how many solute left? 3 solute. So this is what is written, total 4 components, 3 solute and 1 solvent. Let us take an example, salt, sugar and copper sulfate dissolved in water. So this is again the types of solution that we study based upon the number of solute particles. Clear, students? Now there is one more classification of the solution basically based upon the nature. It is gaseous solution, solid, solid solution, liquid solution. So let us discuss about it. See, the types of solution basically based upon the nature is gaseous solution, liquid solution and solid solution. Now it's very simple, students. If you are saying gaseous solution, that means you are taking solvent gas. If you are saying liquid solution, that means you are talking about solvent as liquid. If you are taking solid solution, that means here your solvent is solid. Are you getting my point? Here the name basically is assigned on the basis of solvent that you have taken. If you have taken gas as solvent, it will be gas solution. If you have taken liquid as solvent, it will be liquid solution. If you took solid as solvent, it is solid solution. So this is what I have written. If your solvent is gaseous, but yes, yet again, if you'll see over here, it will be solid and gas, liquid and gas, gas and gas. Getting my point? By this way. So mixture of oxygen and nitrogen, that means gas and gas. Chloroform mixed with nitrogen gas, liquid and gas. Now here solid will come. Solid and gas, that is camphor and nitrogen gas, right? Moving on to the next one, liquid solution. Now that means liquid solution, that means solvent will be completely your liquid. Now if I'll talk about solute, solute can be your gas. So gas and liquid. Example is oxygen and water. Liquid and liquid, that means ethanol and water. Solid and liquid, that means glucose and water. So these are examples of what? Liquid solution. About solid solution, let us talk about gas and solid, that is solution of hydrogen and palladium. Now, liquid and solid, that means amalgam of mercury with sodium. Solid and solid, copper dissolved in gold. Are you getting my point, students? So this is classification, or this is types of solution based upon the nature of the solvent. Clear, guys? Very simple, very easy. Okay. Now, students, moving further, we are going to start with the concentration and concentration terms. Always remember, see students, there are two types of concentration terms. One is temperature dependent, another one is temperature independent. Always remember that concentration terms are of two types. One is temperature dependent, another one is temperature independent. See, the one which is temperature dependent is volume related concentration terms, and the one which is temperature independent is your mass related concentration terms. Okay, the one which contains volume in it will be temperature dependent. The one which don't contains volume in it will be temperature independent. Quite simple case. Now let us talk about one by one, and then you can place in both the categories. That is your homework. You have to place molarity, mole fraction, normality, ppm in all of these examples over here. I have told you what are these. If the formula contains volume, it is temperature dependent. If it does not contain volume, it is temperature independent. Getting my idea? That's great. Now coming to the very first concentration term is mass percentage, also referred to as W by W, or even you can write it as M by M percentage. Mass by mass percentage. What it is exactly? Basically, it is amount of substance dissolved per 100 grams of solution. Okay, for example, if I have to calculate mass percentage or W by W percentage, what it will be? It will be mass of solute divided by mass of solution. Now students, it is basically percentage, so you need to multiply it by 100. So when you are going to multiply it by 100, you are going to get a W by W percentage. Let us take a general example. For example, in any of the book, they have given you 68%, let us say X compound in solution. So what do you refer by this term? So you know the definition, amount of substance dissolved per 100 gram of solution. That means 68 grams. If it is written 68%, so that means 68 grams of solute of X dissolved in 100 grams of solution. Getting my point? So this is the way to read the percentage by using this definition, and this is hence the formula, quite really very important. Mass by mass percentage or W by W percentage is mass of solute by mass of solution into 100. Yet repeating again, solute plus solvent is equivalent to solution. Clear students? In many of the questions, they have given you mass of solute and mass of solvent. They have not given you mass of solution. So you need to add both of them, and then you can put in this formula, you will calculate the mass percentage. Clear everybody? Now moving on to the next concentration term, we have volume percentage. What do we have? Volume percentage or volume by volume percentage, that is V by V. Again, how we are going to define it? It is going to be amount of substance dissolved per 100 ml of solution. That means if I have to calculate volume by volume percentage, it will be volume of solute. It will be volume of solute divided by volume of solution. Volume of solution into what? Into 100 ma'am. Into what? Into 100 ma'am. Clear everyone? This is volume by volume percentage. Moving on to the next, what do we have? We have mass by volume percentage. The name itself says mass is W, by volume is V. So how we are going to define it? Amount of solute, now in grams, dissolved per 100 ml of solution. Why? Amount of solute in grams is W, dissolved in per 100 ml of solution is volume. So W by V. So how we are going to write? See, it is W by V percentage or mass by volume percentage is mass of solute divided by volume of solution into 100. This is mass by volume percentage. This is mass by volume percentage. Clear everyone? Quite simple. Very good. Let us move on to the next one. Now what do we have? We have mole fraction. Mole fraction is represented like this. Now what it is exactly? For example, if we have A component and if we have B component, okay, what is the mole fraction of A component? Mole fraction of A component will be number of moles of A by total moles of A plus B. Okay. In the similar way, if I'll ask you, what is the mole fraction of B component? So it is, mole fraction of B component is number of moles of B by total moles of A and B. Clear? Always remember, if you have been given two components, so mole fraction of A plus mole fraction of B is equal to 1. Is equal to 1. Clear everyone? So ratio of number of moles of solute by total number of moles of solute and solvent is mole fraction. And one more thing, and sometimes in questions they have not given you number of moles. They give you mass. How you are going to calculate? See, always remember. First of all, you will calculate number of moles. N is number of moles. So number of moles can also be calculated as given mass upon molecular mass. This is the formula to calculate number of moles. If you don't know number of moles, calculate from this formula, then equate in all of these formulas. Here you can even mention Gm is your given mass that they will give you in question, and MM students is your molecular mass. Is your molecular mass. Clear guys? So this is all about mole fraction. Moving on to the next concentration term, we have molarity. Always remember, molarity is represented by capital M and the unit of molarity is molar. What it is? Molar. Now what is molarity? It is number of moles of solute per liter of solution. That means molarity capital M is equal to number of moles of solute divided by volume of solution but in liters. So this is the formula for molarity. This is the formula for molarity. Now in many of the questions they have not given you number of moles, ma'am. So how you are going to calculate? You will write molarity is equivalent to given mass of solute divided by molecular mass of solute into volume of solution but in liters. So this is also one more formula for molarity. Now see students, there are two major cases in molarity that you can see. Molarity of dilution, molarity of mixture. So if you have molarity of dilution, for example, let me give you an example. For example, if you have a beaker A which has a volume V, which has a particular molarity. Now you are adding some more volume into it. What will be the new molarity? So this is molarity of dilution. For that you have to use a formula M1V1 is equal to M2V2. M1V1 is equal to M2V2. Now let us take up a case of a molarity of resulted solution. For example, you took a beaker which has a molarity and a volume. You took another beaker which has certain molarity and volume. You are adding them together. So what will be the molarity of the resultant solution? That it is, okay. So one more formula is molarity of resulted solution or a mixture, that is capital M for mixture, is equivalent to M1V1 plus M2V2 divided by V1 plus V2. So this is the formula of molarity of resulted solution. I guess this is clear to each and every one of you. Everybody please write it down. Everybody write it down. Done. Okay. Now students, come about molality. Molality is represented by small m and the unit for molality is molal, M-O-L-A-L. Now they both are different. Molarity are different. What is molality? Number of moles of solute per kilogram of solvent. What was molarity? Number of moles of solute by volume of solution in liter. Here it is per kilogram of solvent. That means what is going to be the formula of molality? Molality is number of moles of solute divided by mass of solvent in kg. Mass of solvent in kg. This is going to be the formula for molality. Clear everyone? That's great. Now students, let us see the next one, that is parts per million. That is also referred to as ppm. Now what is million? 10 raised to the power 6. Okay. Parts per million. So basically it is number of parts by mass of solute present in 1 million parts by mass of solution. See, if I'll ask you what is mass percentage, you will say mass of component by divided by total mass into 100. But here everything is same, but here you will multiply it by 10 raised to the power 6. So it is quite easy. It is mass of solute divided by mass of solution into 10 raised to the power 6. By this way you calculate parts per million. Everybody please write it down. Everybody please write down parts per million. You can even write it number of parts of a particular component by total component parts into 10 raised to the power 6. This is what is percentage ppm. Parts per million. If it is million, then it came 10 raised to the power 6. Clear everyone? Now comes the next concentration term, that is normality. Normality is quite simple. See, normality basically students is number of gram equivalent. Number of gram equivalent divided by volume of solution in liters. So this is what is the formula of normality. And number of gram equivalent you can easily calculate by calculating the equivalent weight with the help of n factor. Quite easy students. I guess now each and every one of you know what is concentration and what are concentration terms. Now we are starting with the topic solubility. What do you feel is solubility? When you are mixing a solute into solvent, it is solubility. No, it is not the correct definition. When you are mixing a particular amount of solute into a particular amount of solvent, that is what is solubility. Solubility, students, is again of two types: solubility of solid and liquid, solubility of gas and liquid. We will understand both of them. Let us start with the very first one. The amount of solute that is dissolved in specified amount of solvent to form a saturated solution at a given temperature is solubility. Yes, amount of solute dissolved in a particular amount of solvent. That is what is solubility. For understanding saturated solution, first of all, let us understand what is dissolution. Dissolution basically is adding solute into a solvent. When it is dissolving, it is dissolution. Now, one time will come that no more solute will add into the solvent. The time will come that no more solute will be able to dissolve into the solvent. That time is saturated solution. When rate of dissolution is equivalent to the rate of crystallization. That is basically your saturated solution, that when no more solute is now added, you are adding, but now they are no more mixing up altogether. So that is what is the saturated solution. Always remember, students, according to Le-Chatelier's principle, according to Le-Chatelier principle, if dissolution is endothermic, solubility will increase. If dissolution is exothermic, solubility will decrease. Quite clear to everybody? Everybody write down. Then we are going to start with solubility of gas and liquid first, and then we will see solubility of solid and liquid. Basically, this is solubility of solid and liquid only. This is your solubility of solid and liquid only. Okay, let me see. Before moving on to solubility of gas and liquid, there are some factors that affects the solubility also. What are the factors? The very first factor is nature. Always remember, polar solute is dissolved in polar solvent. Non-polar solute is dissolved in non-polar solvent. Polar solute cannot dissolve in non-polar one. Okay, and non-polar cannot dissolve in polar solvent. Example of polar solute dissolved in a polar solvent for the case of solubility of solid and liquid. That means here polar solute is solid and polar solvent is liquid. So we can take an example of NaCl and water. Okay, NaCl and water. How does this occur? With the help of hydrogen bonding. There exists hydrogen bonding. Okay, now always remember, non-polar solute is, if you want to take the example of non-polar solute, you can take an example of I2, you can take an example of all the non-polar gases. Okay, I2 in CCl4, okay, in Cl2. So that is what is about non-polar one. Clear everyone? Now second factor was about temperature and heat. So if dissolution is endothermic, solubility increases. If dissolution is exothermic, solubility will decrease. This is about solubility of solid and liquid. Everybody write down. Written. Okay. Now comes solubility of gas and liquid. See, saturated solution already told you. Let us start with solubility of gas and liquid. That means if it is solubility of gas and liquid, that means solute now we are taking as gas and liquid that we are taking as solvent. Yes. So about solubility of gas and liquid, what do you feel? What will be the effect on solubility? What are the factors that basically are going to define about the solubility of gas and liquid? Let me tell you, there is a law, Henry's law, which we are going to cover in this topic, solubility of gas and liquid, which is really very important with regard to your examination, students. Clear? First of all, if you have to explain solubility of gas in a liquid, let us consider we have a closed container. What do we have over here? Ma'am, we have a closed container. Why we are taking a closed container? Because if we won't take closed container, our solute will get, outside. It will move outside. Why? Because it is open. We are taking a gas? No. So basically, this is the liquid and we have taken a gas. So quite easy. For example, if you are providing it certain temperature, if you are boiling it, what will happen? Very easy. If you are boiling it, temperature will increase. If temperature increase, what will happen to kinetic energy of the molecules? Kinetic energy will increase, molecules will move here and there, so solubility is going to decrease. So solubility is going to decrease. What is solubility? Mixing of solute into solvent. It won't mix because you are increasing the temperature. Particles are now moving here and there. Instead of being dissolving, they are moving here and there. So solubility basically decrease. So on increasing temperature, solubility is going to decrease. Very, very, very easy thing that you need to understand. That means temperature is inversely proportional to your solubility. Quite easy, quite simple concept. Now, what are the factors that determine the solubility of gas and liquid? Again, the nature of gas. Polar will be dissolvable in polar only. For example, HCl in water. Example, you can take HCl in water. HCl is a gas. HCl is a gas and water is in the which form? Your liquid form, right? So gas and liquid. So this is solute and solvent. So polar will dissolve in polar only, non-polar will dissolve in non-polar only, polar cannot dissolve in non-polar one. Clear everyone? This is about solubility of gas and liquid. Now it is furthermore explained by Henry's law. Henry's law. It explains that solubility. Now always remember Henry's law is applicable for solubility of gas in liquid. That means you are taking gas as your solute and liquid as your solvent, right? So if I define solubility of a gas in a liquid solvent, it increases and is directly proportional to partial pressure of a gas above solution. See, always remember, solubility we are talking about is directly proportional to partial pressure of the gas above solution. Very, very important key concept that you need to understand. That solubility of a gas is directly proportional to the partial pressure. We are defining solubility as the mole fraction. It is directly proportional to the partial pressure of the gas. Now, when we'll get rid of this directly proportional sign, we will introduce a term that is KH. KH basically is your Henry's constant. It is basically your Henry's constant. See, it's very simple. Now, relationship you need to understand. See, if I am increasing temperature, if I am boiling, what will happen? Kinetic energy of the particles increases. Solubility now will decrease. Again, representing solubility in other terms is mole fraction of solute. So, it is being decreased. So, increasing temperature, solubility decreases. If solubility decreases, students, if solubility increases, or you can say if you're increasing the pressure, you are increasing the pressure, right? So, what are we doing? If solubility is being decreased, what will be the effect on KH? KH will increase. So, always remember, first of all, that temperature is inversely proportional to solubility. Temperature is inversely proportional to solubility, and solubility is directly proportional to Henry's constant. Solubility is directly proportional to Henry's constant. Two major things that you need to remember. Everybody done with this? Sorry, one thing I need to correct it over here. Sorry, please correct this one thing over here. See, if solubility is decreasing, KH increases. So, a solubility is also inversely proportional to KH. Remember this thing? Solubility is inversely proportional to Henry's constant. Solubility is inversely proportional to Henry's constant, students. So, if a more soluble gas has a lesser value of KH, more soluble gas has less value of KH. From this we can conclude. So you can clearly see if solubility is inversely proportional to KH, temperature is inversely proportional to solubility. That means temperature is directly proportional to Henry's constant. So this is also one more conclusion that we can make from these two equations. Clear everybody? Clear everyone? Okay, so this was about Henry's law, students. Do remember this formula because you may observe many of the questions from this one. Now coming to the applications of the Henry's law, let us read the applications, very easy applications. That is solubility of CO2 in soft drinks. You know, when you open basically a soft drink bottle, you observe that there is a gas. The gas is basically dissolved into liquid form. So that is what is solubility. So solubility of CO2 gas in soft drinks. Why we do that? In order it is done, it increases at high pressure. Therefore, their bottles are sealed under higher pressure. So when the solubility is done, it is done under high pressure. Okay, so it is sealed under higher pressure so that it cannot escape outwards, right? Now, see, if you are applying a higher pressure, that means pressure, you have just seen, pressure is directly proportional to solubility. If you apply more pressure, it will become more soluble, no? P is directly proportional to solubility. When we are removing the directly proportion, we get KH. So if you are applying higher pressure, solubility increases, right? Now, scuba divers must cope up with high concentration of dissolved gases while breathing air at higher pressure under water. Okay, this is one more application. Next is at high altitudes. When you go at high altitude, the partial pressure of oxygen is less than that at ground level. At ground level, if you're comparing the oxygen level, it is less than that. This leads to low concentration of oxygen in the blood. Now, it causes a disease because it causes a low concentration of oxygen in the blood and tissues of the people at higher altitude. So, low blood oxygen basically causes climber to become weak and unable to think clearly. Okay, and basically symptoms of a condition are known as anoxia. Clear? So they suffer from these diseases due to that. Now students, we are going to start with the next topic, that is vapor pressure. So very simple thing, what is vapor pressure? Vapor pressure basically is exerted by the surface molecules. It is the pressure exerted by the surface molecules at the container's wall, right? So what actually it is, the pressure exerted by vapors of a liquid on its surface when they are in equilibrium, it is referred to as a vapor pressure. For example, students, if we have a beaker and we do have a liquid solution over here, we know that there are two kinds of particles. One are these particles which are the surface molecules. These are your surface molecules. Okay, and there are some more particles which are present inside. These are your bulk particles or your bulk molecules. My just simple question is, which of the following is going to exert pressure? But obvious, ma'am, it is very clear that surface molecules are going to exert pressure, not the bulk one. Why? Because bulk one are having force from all the direction, but surface one are having force only from the lower direction or from the side ones. So they exert some pressure onto the walls of the container and on the surface as well. That is what is vapor pressure of a solution. Yes, everyone. So that is what is the vapor pressure of a solution. Now students, factors is quite simple. Factors, pressure and temperature that affects the vapor pressure. If you are increasing the temperature, what will happen? The kinetic energy will increase. They tend to move outward, so they will exert more pressure. So this is what is a vapor pressure. Factors that affect it. Now when you're increasing the pressure, that means you are applying a force from the top, right? So by this way you have to understand it in depth. You have to visualize it and in actual how it is taking place. So now we are going to start with two cases over here that is in your examination and is really very important. The very first is case A, in which solute and solvent both are volatile. Now what is a volatile state and what is a non-volatile state? Let us understand. Volatile is something which exerts vapor pressure. Okay, now see, we basically know we have a solvent. Let us consider we have a solvent with us. Okay, this is solvent. And solvent, let us consider it is A. A is your solvent. So this is A particle, A particle, A particle, A particle, A particle. I already told you that only basically surface particles will exert the pressure. So when it is exerting pressure, remember you have to take a closed vessel. Otherwise, pressure won't be exerted, right? So it is exerting some pressure. Let us consider it is exerting a pressure that is P naught A. Now what is P naught A? P naught A is pure vapor pressure of solvent A. Now what is pure vapor pressure? Pure is when something is not added into it. So P naught A is pure vapor pressure of solvent A. Now in this, what we are adding? We are adding a solute. What we are doing now? We are adding, ma'am, a solute. Let us consider we are adding B solute over here. What we are doing? We are adding a B solute over here, right? And I am considering that solute also is your volatile. Solute is also volatile. So it is also exerting pressure. Volatile is something which exerts pressure. So it exerts in pressure of P naught B. Now what is P naught B? P naught B is pure vapor pressure of B. Now they both will combine and what they will form, ma'am? Very simple. They both will form a solution. What they will form? They will form a solution. Solution is comprised of solvent and solute. Solvent is your A, solute is your B. That means how it is going to look like? Ma'am, it is your A particle, your A particle, your A particle, and here will be your B particle, your B particle. Now both of them will be exerting force after combining. B will exert now force of PB, and orange ones, A will exert a force of PA. Now what is PA and PB? PA is now vapor pressure of A in solution, and PB is vapor pressure of B in solution. Okay, so how you're going to do is, do remember according to Raoult's law. Now which law I am taking name over here? Raoult's law. According to Raoult's law, PA is the new pressure when both of them have combined. PA is equivalent to P naught A into mole fraction of A. And what is PB? PB will be equivalent to pure pressure of B into mole fraction of B. These are the values of both of them, and when you both add them all together, it will be total pressure. So total pressure is PA plus PB. That means it is going to be P naught A XA plus P naught B XB. So this is very important formula that we have derived from the Raoult's law with the help of Raoult's law. Everybody please write it down so that we can move on to the next part. This is Raoult's law for volatile solute and volatile solvent. Clear everyone? Clear everyone? When solute and solvent both are volatile, write this formula and these two also. This is from the Raoult's law. This is from which law? The Raoult's law. Now student comes when you are taking non-volatile solute and a volatile solvent. Non-volatile is something which do not exert any pressure. Now let us understand students, this is our solvent again. So solvent is again your A particles. These are again your A particles. These are again your A particles which are exerting some force which is basically P naught A. What is P naught A? Pure vapor pressure of solvent A, right? Now what you are going to do, you are going to add into it solute which is non-volatile. That means it is now not going to exert any kind of pressure. So that means this is B particles, it won't exert any pressure on the walls of container. So they are not exerting any force. You are adding both of them together. What you will form? You will form a solution. Now what you are going to form? Ma'am, we are going to form a solution. Solution comprises of solute and solvent. Solute over here is your what? Solute over here is your B particles and solvent is your A particles, right? But do remember, here we have A particle, B particle, A particle, B particle. See, this is a mixture. Only A particles are exerting force PA because B are non-volatile, so not exerting any force. So just tell me, if I have to write the total solution pressure, we know it is equal to PA plus PB. We know PB value is 0 because it is not exerting force. That means total pressure is equivalent to PA. And what is PA? PA is P naught A XA according to Raoult's law. What is P naught A? Pure pressure into mole fraction of A, right? So if I'll ask you the total pressure for non-volatile solute and volatile solvent will be this one now. Clear? Now I have told you two formulas for volatile solute and volatile solvent and for non-volatile solute and volatile solvent. Now comes our ideal solution. See this, from this case, no, you are going to derive the very first colligative property also. So till now write it over here. When we are going to discuss the colligative property, I will come back to this slide again and I will let you know how they are interconnected with each other. Clear everyone? Okay. Now students, comes about ideal solution. What is an ideal solution? See, basically this is our Raoult's law, again telling you this is our Raoult's law. This is our Raoult's law, that PA is equals to partial pressure of a component is equivalent to the pure pressure of a component into its mole fraction. Clear everyone? So now coming to what is ideal solution. Ideal solution is basically the one which follows a Raoult's law. So what are the conditions for a solution to be ideal? It should follow Raoult's law. Now very easy thing I am telling you, it should follow Raoult's law. What is Raoult's law? That partial pressure of a component is directly proportional to mole fraction of that component. For example, PA is equivalent to P naught A into XA. If you'll get rid of this directly proportion, you will introduce the pure pressure. Similarly, PB is equivalent to P naught B into XB. Here, PA is partial pressure of A. P naught A is pure pressure of A. It is mole fraction of A. Similarly, you can write for B, students. So this is what is Raoult's law. Now, what are the conditions for an ideal solution? Always remember, students, ideal solution basically in this case, you are going to see that you know that here, see for example, this is your A component. You are adding it with B component. You are forming AB solution. So here interactions of AA component, that means AA particles, BB particles and AB particles are same. Interactions are same. Second key point, delta H mixing for all of them is equal to 0. Third case, delta V mixing for all of them is equal to 0. Delta H mixing and delta V mixing for all of them is equal to what, ma'am? Is equal to 0, everybody. Everybody please write it down about ideal solution. Clear, everyone? Okay, now students, now comes examples of ideal solution. It is benzene and toluene, ethyl bromide and ethyl chloride, N-heptane and N-hexane, chlorobenzene and bromobenzene, ethyl iodide and ethyl bromide. Clear, everyone? Clear everyone? Now students, there is a graph of an ideal solution that I am going to prepare over here. See, we have just done right now. It is very easy graph. See, what you have to do is, this is a graph for ideal solution. Here I am going to take vapor pressure. Here I am going to take mole fraction. Okay. Here I will take mole fraction of A component and mole fraction of B component. Here I will take it as 1 and it as 0. Why? Because we always know that mole fraction of A plus mole fraction of B is equal to 1. If you're taking 1 as 1, so another will be 0 automatically. So at this point, I will take mole fraction of A as 0 and here I will take mole fraction of B as 1. So at this point of time, what will be the vapor pressure? Let us consider, students, very simple things I am explaining you. So no need to, get confused in all of these things. Here I am considering that PA basically is greater than PB. Okay, I am making a graph where PA I am considering is greater than PB. Here, P naught A is greater than P naught B. Let us consider pure pressure of A is greater than pure pressure of B. Now see students, at this point of time, what is total pressure? Total pressure is PA plus PB. What is PA? PA is P naught A XA, XA is 1 into P naught B into XB, XB is 0. So this is 0. So total pressure is equivalent to P naught A. And we know that P naught A is more than P naught B. So we are considering it as P naught A over here, right? Now at this point of time, let us write at this point of time, total pressure is equal to partial pressure of A plus partial pressure of B is equivalent to P naught A into XA is 0 plus P naught B into XB is 1. So now this is 0. That means total pressure is equivalent to P naught B. We know that P naught B is less than P naught A. So if you have taken it a higher amount, write P naught B over here, which is at a lower now, right? So if I am saying that this curve, let us join these. This curve basically is curve of whom? This curve is basically a curve of PA is equivalent to P naught A into XA. And this curve basically will be, this curve will be basically of P naught B XB is equivalent to PB. These are the curves for partial pressure. And when you join both of them together, this will be a curve for total pressure, that is PA plus PB, that is P naught A XA plus P naught B XB. right? So this is the graph for your ideal solution. Clear? Now students, let us start with non-ideal solution. Now in non-ideal solution which do not follow Raoult's law, first thing. Second thing, delta H mixing is not equal to 0. Delta V mixing is not equal to 0. Clear? This is non-ideal solution. Now in non-ideal solution, always remember total pressure is not equal to P naught A XA plus P naught B XB. Yes, everyone. Now students, there are two kinds of deviation that you will see in non-ideal solution, positive and a negative deviation. So in a positive deviation, total pressure is more than P naught A XA plus P naught B XB. And these are the examples of positive deviation, that is carbon tetrachloride plus benzene, carbon tetrachloride plus chloroform, acetone plus carbon disulfide, acetone plus ethyl alcohol, and acetone plus benzene. If I'll take examples of negative deviation, that is chloroform plus acetone, chloroform and benzene, chloroform and diethyl ether, and acetone and aniline. This is of negative. In negative deviation, total pressure is less than P naught A XA plus P naught B XB. If it is more than this, no, so the graph that you are going to obtain, for example, this was your graph, right? This was your expected graph that you have just seen right now. Right, this was your graph. For a positive deviation, each and every value will be more than the initial value. So this is going to be the curves. Orange one will be the positive deviation graph. If everything is more than that, right? Now, if everything is less than the initial values, so how will the graph look like? Let me show you. How will the graph show like if everything value is less? How less? Total pressure is less than this, okay, plus this sum. So PA will be less than P naught X, PB will be less than this. If everything is less, so the graph for negative deviation is going to be like this. This is the graph for negative deviation. Everyone do write the examples over here. Everyone do write the examples over here. Clear? Now students, moving on to the azeotropic mixture. There are two kinds of azeotropic mixture. One is with the minimum boiling azeotrope and one is with the maximum boiling azeotrope. Let us understand this in depth. It is very easy, students. What is azeotropic mixture? First of all, understand this. Azeotropic mixture are the binary mixtures which having the same component in liquid and vapor phase, and both of them will boil at the constant temperature. Again repeating, when they have a same component in liquid and the vapor phase and they are boiling at the same constant temperature. So this is what is azeotropic mixture, and non-ideal solution will always form azeotropes. So here you have to see if there is a large positive deviation. Let us consider if there is a positive deviation, then it will form minimum boiling azeotrope. Minimum boiling azeotrope when there is a positive deviation. In the case of negative deviation, it will form a maximum boiling azeotrope. So minimum boiling azeotrope is seen in the case of large positive deviation, and basically it will boil at a temperature which is basically lower than the boiling point of its component. Example you can take is ethanol and water. When there is a positive deviation, minimum boiling azeotrope. When there is a negative deviation, maximum boiling azeotrope, and that is very, very important example, very, very important for the maximum boiling azeotrope, students. That is water and HNO3. Again and again asked in question papers, again and again. What it is exactly? When you are going to take a negative deviation graph, it will form a maximum boiling azeotrope and it will boil at a temperature greater than the boiling point of its component. Always remember. Clear, simple, easy. Moving on to the next is colligative properties. One colligative property though we have already done, but yes, now coming to the next one. Colligative property, basically colligative properties are used in order to determine the number of solute particles. It depends upon the number of solute particles only. Okay, so the property of ideal solution which depends only upon the number of particles of solute. Only solute particle. It will depend only and only upon the solute particles dissolved in a definite amount of a solvent and does not depend upon the nature. Again repeating, only and only will depend upon the number of solute particle. Always remember here solute that you are taking, in order to a substance to exhibit colligative property, solute should be non-volatile. Do remember that. Solute should be non-volatile, then only colligative property will be applied. So these are what is colligative properties. There are 4 colligative properties that you have to study. The very first that you are going to see is relative lowering of vapor pressure. The second one is elevation of boiling point. The third one is depression of freezing point. And the last one is osmotic pressure. Osmotic pressure. So let us start with the very first one, that is relative lowering of vapor pressure. That though I have already explained you, let me show it to you over here only. When we have taken a case of non-volatile solute and volatile solvent, what it is exactly, what is relative lowering of vapor pressure? Just tell me. P naught A value is more than PT. Do you agree with this? Why? Pure pressure of solvent is more than that of solution. Why? Because see here 6 molecules are exerting pressure, but in solution B are not exerting, only A are exerting, and only there are A molecules, 2 A molecules which are exerting. So there are more numbers. We told that colligative property depends upon the number of solute particles or the solvent particles, only solute particles, but here number depends. What I want you to explain is, you have to see how many particles are exerting force. Here 6 particles are exerting, here only 2 particles. B is not exerting, only A are exerting. There more particles are exerting, so that pressure will be more, right? So basically, what is relative lowering in vapor pressure? How much value is being lowered? So that means if I'll ask you the lowering of vapor pressure, that is P naught A minus PT, and you know PT is PA only, right? So this is lowering. This is lowering in vapor pressure. If they ask you what is lowering in vapor pressure, that is P naught A minus PT, or you can even say P naught A minus PA. Why PA? Because PA basically is equivalent to PT when we have calculated the terms. What is relative lowering in vapor pressure? It is P naught A minus PA divided by initial pressure. This is relative lowering of vapor pressure. P naught A minus PA by P naught A. Initial value, you have subtracted the final value, divide by initial value only. That is the relative lowering. What is lowering? How much it is lowered, how much it is decreased. So P naught A minus PT. PT is PA, so P naught A minus PA is lowering. And what is relative lowering? This is. And now coming back to my topic over here again, my formula is very simple, students. P naught A minus PA by P naught A is equivalent to XB. What is XB? Now XB is number of solute particles. I already told you colligative property is the one which depends upon solute particles. So it depends upon the mole fraction of solute particles. This is the formula for relative lowering of vapor pressure. Relative lowering of vapor pressure. If it is very dilute case, let us consider. Let me write the complete formula first. P naught A minus PA by P naught A is equivalent to N2 by N1 plus N2. This is how I am going to write the mole fraction of B. But if it is very dilute, for very dilute case, students, the formula changes. Formula will be P naught A minus PA by P naught A is equivalent to N2 by N1, students. Is equivalent to what? N2 by N1, everybody. Everybody please write it down so that we can move on to the next colligative properties of ours for now. Yes, everybody, done. Very good, students. Very good, students. Now, students, comes our next colligative property, that is elevation and boiling point. Very simple. The things that you need to remember over here is, see, vapor pressure is inversely proportional to boiling point. Now, see, for example, if I am showing vapor pressure over here and I am writing temperature over here, we know that vapor pressure of solvent is more than the total vapor pressure of solution. We have just seen vapor pressure decreases in that case. So I can make a graph. I will say this is the vapor pressure curve for pure solvent. For pure solvent. And I say that vapor pressure decreases for solution. So this will be a curve for solution. So if I am going to mark both of these points, now at this particular temperature, if I am seeing the vapor pressure at this particular temperature comes out to be, this is a pure solvent. Now pure solvent, if it is pure solvent, is P naught A. The temperature will be what? T naught B. I am talking about boiling point, so it will be T naught B. Pure boiling point of solvent. Now for solution, if I have to see, I will extend this line. I will take out, this is going to be TB, right? TB. So what will be delta TB? Delta TB will be TB minus T naught B. What is TB? TB is boiling point of solution and T naught B is boiling point of pure solvent. I now only told you this thing that vapor pressure of pure solvent is more than solution, so it is upward. But if you'll see the boiling point, TB is more than T naught B. That's why I told you vapor pressure inversely proportional to boiling point. Vapor pressure of solvent is more, so boiling point will be less. Vapor pressure of solution is less, so boiling point will be more. So always remember this is delta TB. This is elevation and boiling point, and this delta TB, students, is directly proportional to molality. Why? Because colligative property depends upon number of solute particles. That means if I am going to get rid of this directly proportional sign, I will introduce KBM, molality. This M is molality. So here are my two formulas for elevation and boiling point. Everybody please write it down. Everybody please write it down. Yes, students, everybody have written this. Shall we move on to the next colligative properties of ours? This is elevation and boiling point. Now, students, there is one more thing. There is one more thing. I have now only told you a term KB. What exactly is KB? Here you need to understand. KB is basically molar elevation constant. What it is? Molar elevation constant or ebullioscopic constant. What it is? Elevation and boiling point observed in one molar solution of a non-volatile solute is called molar elevation constant. You can even calculate KB, but let me tell you, in question paper, the value of KB is provided to you, but still I am giving you this formula. KB is equals to R into TB square into M divided by 1000 into delta H vaporization. Clear, everyone? This is elevation and boiling point. Now I am going to start with depression of freezing point, but before that, everybody please draw this graph so that we can move on to the depression and freezing point. Everybody draw this graph so that we can move on to depression and freezing point. Done? Done? Now let us talk about depression and freezing point. In the case of freezing point, students, curve is like this. This is for solid, this is for liquid, something kind of this curve. Now this curve is basically for your pure solvent. Again, here you are going to take vapor pressure, here you are going to take temperature. Now, if I have to draw the curve for solution, we know that vapor pressure of solution is less than solvent, so it is like this. So, this is for solvent. Right, everyone? So, it is basically touching the solid curve over here and here. So, this basically is temperature of pure solvent, T naught F. And this is for here you have to write solution. Let me write it again. Here solution will come, no? Because vapor pressure of solution is less than that of solvent. So now it is touching solid over here. So this curve, what is basically freezing? Freezing is basically when you are converting liquid into solid, no? So we have taken these two curves over here. This pure solvent is touching over here, so this is T naught F, and this solution is touching, so this is TF. So what is delta TF? Delta TF is change in the freezing point or depression in the freezing point. It is T naught F minus TF. Clear? Just as opposite of the case of boiling point. In boiling point, you have seen boiling point was increasing of solution because vapor pressure was inversely proportional to boiling point, but freezing point is decreasing, right? So basically, this is the formula. Always remember, delta TF is directly proportional to, again, molality. If you'll get rid of this directly proportional sign, you will introduce KF over here, and this is the formula. So these two are the formulas. Clear, everyone? Now over here, what is KF? You basically should know. KF basically is your depression of freezing point observed in one molar solution of a non-volatile solute is KF. How you can calculate KF? This is again the formula. They won't ask you the formula, but yes, for your information, I have written it over here. Everybody please draw this graph so that we can start with the last colligative property of ours. Yes, everyone. Please do it fast so that we can start with the last colligative property of ours. Done, everyone? Now, students, come the last colligative property, that is osmotic pressure. See, what is osmosis? In order to understand osmotic pressure, we should know about osmosis. In order to understand about osmosis also, see, osmosis is seen when we insert a semi-permeable membrane into a solution. For example, I have C1 concentration over here, C2 over here. And I say that C1 is more than C2. When I am saying my concentration is more of a particular substance, if C1 is more, that means over here solute is more and solvent is less. And in this case, solute is less and solvent is more. Okay, so what is osmosis? Osmosis is the movement of solvent particles from a lower concentration to a higher. Lower concentration is C2, and here why it is, if its concentration is lower, that means solute is lower and solvent is higher. So osmosis is movement of solvent particles from a lower concentration to a higher is osmosis. So what is osmosis? The spontaneous flow of solvent through semi-permeable membrane from pure solvent to solution, from a dilute solution to a concentrated. As per your observation, you can say any of the definition. It is osmosis. Now what is osmotic pressure? The pressure that we apply, right? So basically the pressure required to be applied on the solution to prevent the flow, to prevent the inflow of solvent into the solution is your osmotic pressure. Yes, everyone? Now students, what is the formula for this particular part? See, the formula is pi V is equivalent to nRT. Pi basically is your osmotic pressure, V is volume, N is number of moles, R is gas constant, T is temperature. Now, what is isotonic, hypertonic and hypotonic state? Isotonic is solutions of same osmotic pressure. When there is same osmotic pressure, that means when pi 1 is equivalent to pi 2. Osmotic pressure of first is equivalent to osmotic pressure of second. Hypertonic is when solutions having higher osmotic pressure, and hypotonic is solutions which having lower osmotic pressure. So in one of the cases you may have seen that when water moves inside, and when water moves inside, swelling occurs, and when water moves outside, it shrinks out. So that is hypertonic and hypotonic cases. Clear, students? Now students, there is one more definition of reverse osmosis. What is reverse osmosis? Basically the RO concept, right? So when a pressure greater than that of osmotic pressure on the solution side we apply, then solvent from the solution flows into the pure solvent. Now see, basically what happens, initially the solvent was moving from lower to higher. Now we are applying a certain amount of pressure on the another side, so the other particles also come in onto the another side. So that is reverse osmosis. That movement now becomes from the opposite end. Okay, this is reverse osmosis. Now students, come the last part, that is abnormal molecular mass. Before that students, before starting the abnormal molar mass, write down the formula fast so that we can now end up with our today's session. Yes students, everybody please write it down so that we can start with the last part. Okay students. Now, there are some substances in which we have seen that molar mass values are different, right? So, for that we calculate Van 't Hoff factor, that is I. What is I? I is basically the experimental value of colligative properties divided by the calculated value. See, when you calculated, you know colligative properties, okay? See, when you are seeing the colligative properties, you were applying for non-volatile cases, okay, solute. But there are some substances in which we have seen electrolytes. All of these cases which you have done till now, all of the formulas you have applied for non-electrolytes. But when it comes for electrolytes, when it dissociates into its ions, which formula you are going to apply? The mass is going to be different for that cases. That is abnormal molar mass. Because for electrolytes, the value becomes changed for each and every colligative property. So we introduce the term I. What is I? I is Van 't Hoff factor. It is experimental value of colligative property divided by calculated value of colligative property. So by this way you can calculate the value of I, okay? And in each of the formula, for example, the very first formula was XB is equivalent to P naught A minus PA by P naught A. Now you're going to multiply it with I. Similarly, you have next formula. Delta TF is equals to KF into molality into I. The next formula, delta TB is equals to KB into molality into I. The next formula you have. So by this way you'll multiply with Van 't Hoff factor for the case of electrolytes. So how you're going to calculate if you have association and dissociation, that is alpha, that is the dissociation moles is equivalent to I minus 1 divided by N minus 1. Clear everyone? Clear everyone? Very simple. I, you can easily calculate. I is total moles after dissociation divided by total moles before dissociation. This is one more formula through which you can calculate all of these. So students, by this way, we end our today's class over here. I hope so you have completed the whole chapter in this particular session. Now it's time to practice all the questions based upon the formulas. Always remember, I will only be introduced for the case of electrolytes, and for non-electrolytes, you have to follow the same formula that you have done for colligative properties. Right students, now we shall be meeting in the next session. Till then, keep smiling, keep learning. Thank you so much and have a good day everybody.